All right, good morning, everyone. So today our lesson's going to be on linear combinations of vectors. Okay. All right. So first we're just going to go over some terminology. It's mostly just recap because we've already talked about this earlier in the unit. So recall that collinear vectors are when I have a vector that's equal to just another vector multiplied by some scalar constant, right? So basically I can just, one vector is a multiple of the other. So like let's say v is twice as long as u, so m would just be equal to 2 in that case. And I have the same thing for when I have a third dimension, it would be coplanar vectors. And I would have a similar idea here. So I could have like vector w is equal to a times vector u plus b and then vector w. Okay? And these are linearly dependent. Okay? All right. So now that we've gone over that, non-coplanar vectors that form the basis for space are linearly independent. Okay. Right. I'll just recap from earlier in the unit. So based on that, we'll have our theorem that if I have three different vectors, u, v, and w, if I take the cross product of u and v, sorry if I'm writing a little bit small, make that a little bit bigger, but the cross product of u and v, and then dot it with w, and it's equal to 0, then my three vectors, u, v, and w, are coplanar. All right. And using all this information, we can do some examples. So today's lesson, even though it's technically a new lesson, it's essentially just taking some of the properties and theorems that we've talked about earlier in the chapter and then kind of put aside for the time being, or we've used them a little bit, but not in a very major way. We're applying them more today. So, example 1, let's try these out. So, determine which pair of vectors are collinear. Okay. Using the properties from above. So, try it on your own first. So hit a quick pause on the video, but then once you're ready, or maybe if you get stuck a little bit, unpause so I can take it up. So part A, I've just got vector u. Oh, sorry, you would have to pause after I actually give you the vectors, not beforehand. So after I read out the vectors, now pause it and give it a try. So that's part A, and then my two vectors for part B. So So now give these a try and unpause the video when you want to see the solution. All right, so let's take up the first one. So we're going to let, using our theorem from above here, right? They are collinear when I can write one vector as the other vector just multiplied by some scalar value, right? Like 2, 3, 4, whatever it may be. And we have to make sure that it works for both our components, right? Whether we have just an I and a j component if it's working in 2 dimensions, or I, j, and k if we have 3 components. So we're just going to let vector u, or sorry, vector v, my apologies, it's pretty late, so I'm going to maybe misspeak by accident, but I'm going to let vector u um, be multiplied by m to give me vector v. And now we're just going to calculate what m is and see if it's the same value for both our I and our j component, then we can get this to work and they'll be collinear. If we get two different values, so like we have a different value for what we would have to multiply our I value to make it work versus our j value, then we can't really have that, right? It has to be one scalar value. So that's what we're going to do. It's going to be negative 4 and 14, so one of our given vectors, is equal to our constant that we don't know yet, or our scalar, I guess would be better to say, um, multiplied by our other vector. So then from here we get two equations, right? We get minus 4 would be equal to 2m, right? The I components would have to be equal to each other. And then the same logic would apply for the j components. The 14 would be equal to negative 7m. And now we would calculate for m. So doing a little arrow over here on the side, obviously very straightforward. We just divide both sides by 2. So m would give me negative 2. And doing the exact same thing here, 14 divided by negative 7 would also yield a value of negative 2. So because those two have the same value, my m value is going to be negative 2. So basically, vector v can just be written as minus 2 times my vector u. So therefore, they are collinear. All right. Now let's try the same thing for part B with our two three-dimensional vectors. See if that works for us. The idea is exactly the same. Now I'm just going to have three equations to solve instead of two. But again, they're simple, just one-step equations, so there's nothing to worry about. So let's let v equal to mu, same idea, and we're looking for now, instead of the scalar that we're multiplying by to be the same just for these two, I need it to be the same for all three equations. So I can't just stop if, like, hypothetically the first two match. So let's write this out. I've got my first vector of negative 1, comma, 2, and 15 will be equal to m times 2 minus 4 and 10. So now we've got my three equations. Negative 1 will be equal to 2m. 2 will be equal to negative 4m. And then 15 will be equal to 10m. And now we solve each one individually. So I'm just going to put my arrows here. Careful, that's not a vector arrow. Just moving on to my next step. Dividing both sides by 2, nice and straightforward. M here would give me minus 1 over 2. Let's see if our second equation matches. 2 divided by negative 4 gives me negative 2 over 4, but that just simplifies to 1 over 2. So I've got a little bit of hope here. These two match. If my third m value is also negative 1 over 2, then we would have our two vectors be collinear. So, sorry about that. M here would just be equal to 15 divided by 10, which wouldn't give us the same thing, right? 15 divided by 10. Number one doesn't even have a negative value, so no matter what this simplifies to, it's still not going to match. But even its value, it's not what we need. It's 3 over 2. So vector v cannot be written as vector u multiplied by some value of m. So therefore, u and v are not, let's do all capitals, not collinear. Okay. All right. So, of course, if you have any questions, I'm obviously not here right now because that's why there is a recording in the first place, but I'm happy to answer questions when I return. So let's move on to our next examples. What else can we do with the properties that we talked about? So we can do proofs. I know we did some proofs yesterday using vector properties, but we can also do it using the properties that we listed on the page above, or yeah, the previous page. So let's do example 2. So show that the vectors u is equal to minus I plus 3j and v is equal to 2I plus 4j, 4j are coplanar. Okay? So that's the first part of our question. And then after that, we're going to write x, so vector x, as a linear combination of u and v if vector x is 5, 8. Okay? So here's the question. I actually am going to cut this video and put the solution in another video just so that each individual video for this lesson doesn't get too long. So give it a try and then open the next video in the playlist for this lesson and then see what the solution is.